and thanks for having me here. I've been in recent years. I've been not just looking at server and networking. I've been looking at edge computing and cloud native and the networking aspects of it. Basically, as you know, the edge computing is basically where your resource is constrained and you want to do more with less, right? And it's less latency sensitive application. That's where and most of the edge computing platform typically runs Kubernetes, right? That's where we're looking at different CNIs, and one of the CNI that we wanted to use was, and we tried it out, was Calico. I know people talked about, I think Dushyant and even Brandon talked about Cilium, right? There is another CNI in Kubernetes, which is Calico, which also is trying to use eBPF. So I'm going to talk about how the eBPF data plane is driving the Calico development in the recent years, and in general about what is Calico and how it's used and what is the benefit you're going to get and what is the exact places where the Calico is actually benefiting in terms of performance as well as latency. Okay. Okay, so as some of you might know about Calico, so Calico is basically primary purpose of that is a container networking and security. Okay. So it's basically a CNI for Kubernetes, right? So if you typically take Kubernetes, it's a resource orchestrator or a resource manager, right? You have a CPU, you have memory, you have network as a resource. It needs some kind of a model, or it needs some kind of a plugin to manage your traffic, right? That's where the CNI is, right? And Calico provides those kind of plugins to manage your traffic between the pods or between your services and between the nodes as well, right? But the Calico started prior to Kubernetes. So Calico was there, or the project was started when we had technologies like OpenStack and other technologies. So it predates your Kubernetes. So it not just provides the CNI, right? It gives you a advanced networking policy model, okay, which is much more than what a Kubernetes typically mandates for managing your CNI, right? So typically what this Calico is, right? Calico is like a control plane, okay, through which you can configure the network policies and network configuration and program it to a data plane, right? And the data plane goes and executes that and performs the required policy changes to make sure that the container pod-to-pod communications all everything is fine. Sorry, I'm moving. Okay. So the Calico supports multiple different data planes, not just the eBPF, right? So since it predates Kubernetes, it was already supporting Linux, so it was supporting IP tables, which was there from last 25 years. So in the IP tables, typically it's provided by the kernel, and Calico applies all the policies and the rules depending on the way you're forming your clusters and etc. Right? And the second one that Calico supports is the eBPF, which I'm going to talk about it. Right? So in this, the Linux provides you the environment to run the eBPF code, but the Calico gives you the actual code and implements the data plane that actually applies that particular hooks and etc. Right? And there is another data plane which is completely user-based, which is VPP based, which is the framework developed under FDIO, okay, which is based on the Intel DPDK, and that's, I think, the project have been started and still in alpha stage kind of a thing. I mean, it's still in work in progress, right? So that's the third one. Fourth one is, I think we talked about Windows doing eBPF, and so if you are having a Windows nodes in your Kubernetes, Calico does apply all those policies, everything that you typically get in Linux can also be applied on the Windows. And yeah, Windows. Sorry about that. So Windows eBPF, which is trying to be more compatible with Linux eBPF. So you should be able to get the same benefit that you're getting on the Linux with Linux eBPF on Windows as well, right? So, okay, I'm also going to touch upon what is eBPF. Since, as Brendan said, everybody will have their own understanding of eBPF, so I'll just touch upon this so that we can then move on to the eBPF data plane, right? So from our perspective, okay, it basically gives you a sandbox where you can run a program and configure your kernel at runtime. So basically it allows you to customize your cluster at runtime, right? And another good thing about it is it makes sure that the program that you're writing doesn't crash your kernel, right? and it has checks and balances to make sure that okay, it is verified and it performs what you want to do. Like you don't want to add too much code which crashes your kernel and etc. Right? And there are like supporting helper functions which you can use to customize your kernel. And finally, you can use any compilers. I think there are like Python based also. You can write a eBPF program today, right? And finally, you can or you can directly write into bytecode if you know how to write it, right? So that's essentially is eBPF. I'm just skipping it. So what sort of things that the eBPF can do, right? There are multiple different use cases that we can come up with from an eBPF perspective. From a Kubernetes perspective, the three things that are key is security, logging and tracing, and the networking, right? I think Dushyant talked about networking a lot, like what's the benefit that Kubernetes is going to get. I'm going to touch upon a bit more on that. Coming to the security, I think it depends on what you apply for, right? For example, if it's an edge computing, right? You typically run heterogeneous application, and you want to know if one application is not actually like calling the system calls which you are not supposed to call, right? Those kind of things can be done with SecCom, where you can write the programs to make sure that okay, you're not calling the system calls which you're not supposed to do. Those kind of things can be done. Logging and tracing, I mean, I think one of my colleagues is going to talk about more on logging and tracing, where typically you can gather more information. For example, there is a project called Kepler where you can use this eBPF hooks to get the per program level metrics and then apply AI on top of it to look at okay, what's my power consumption or what else I can do it, right? Those kind of logging. And you can also write programs to trace whether my application is performing or I can tune my application, right? Where I'm spending more time. So those kind of use cases can be enabled. And networking, so as Dushyant said, you can have hooks at different places in your networking stack, and then you can add advanced features as well as you can improve your performance as well. So before we go into the eBPF, let's reflect upon the IP tables itself, right? I mean, IP tables has been there from like so long, and why do you need another data plane, right? So what are the advantages of eBPF? It's well understood. That basically means if I do an IP tables, it just lists on the IP tables and it's recommendable. We know what exactly it's doing, okay? And what is the services it's providing. Like if Calico programs certain things into the IP tables, you can just look at saying that okay, how is my packet going from one port to another port, okay, is there a DNAT and all those things. You can just dump it and you can see it in the client side, right? But the majority of heavy lifting is done by Linux, where it takes care of protocols, routing, and all those is taken care by the Linux networking aspect. And it's well tested. It's been there for like everybody would have actually used the IP tables, so it's well tested, right? Even though it has a lot of advantages, it has its own drawbacks as well, right? It does not scale. So when I say it does not scale, for example, if you have a cluster where you are running thousands of services, right? So which means that I'll have rules, so many rules, right? So the search operation complexity will be around ON, right? So any services at the end of your IP tables will suffer, right? So it's hard, and it is not extendable, which basically means if I want to change anything in your IP tables, either you have to change your Linux subsystem or you have to write some kind of a plugin, which typically customers might actually say, okay, I don't want to run anything which is not part of your kernel or not a standard way of doing it, right? And IP tables is a shared resource, right? So typically you have Calico writing certain policies into IP tables, kubeproxy is writing certain things, and others are also writing certain things into your IP tables, right? You need to maintain the consistency. Okay, you need to make sure that okay, the rules are properly updated and there is a consistency between the entire all the things that are actually writing into the IP tables, right? So this is essentially drawbacks of the IP tables. So why Calico is using eBPF, right? So one, with respect to container, it wants to scale the services. So with eBPF hooks and everything, that's optimization you're going, your search operations reduces from ON to O1. So which basically means if I'm running a thousands of clusters, my search operation is getting, complexity of my search operation is reducing, which basically, and it allows you to bypass certain Linux networking like IP tables, right? Which will improve your performance and reduce your latency. Especially this is true for edge computing use cases where you want to have as much less latency as possible, right? So and improving the performance also helps in the edge computing, right? And in eBPF, in Calico eBPF, the kubeproxy functionality is integrated into the eBPF data plane itself, which basically means There is no clash for the shared resources. There's one guy who is actually writing all the rules, writing and managing your backend IP addresses and etc. Right? And with eBPF extension, you can write more features, which is more like customizable for that particular customer or for that particular features that you are adding, which may not be upstreamable. You can still write the functionality and provide that as a service, but you don't have to like upstream it, right? Because it might be customized to specific use case, and people might not like accept it in the upstream. So that, those extension can be done with eBPF. Okay. So what is the eBPF data plane concept with respect to Calico, right? Typically, you attach from Calico perspective, we attach the program at two places, right? So for two things, one is for devices and for the system call, right? So for the device, you typically attach at an ingress and a egress point. As Dushyant talked about, you can attach at a TCE point, right? The program that you attached, the Calico, when the packet arrives, it has a chance to look at the packet and look at, okay, what should I do with that packet? So it can modify the packet and it can route it according to the policies that have been set, and it can either accept it, drop it, or forward the packet, right? For example, if your service is not running on the same node, you can choose to transfer it to the neighboring node where the your service is running, right? And typically IP tables are often bypassed here, right? And the other place where we attach it is the system calls, right? Where you can typically read your syscall arguments or modify your syscall arguments, which means the program A wants to connect to a point B, but you can write a program, say, okay, that is not the point where you need to supposed to be connected. You are supposed to be connected to another point, right? Those kind of are the concepts that the Calico eBPF has built on. Okay, so before we go on, let's look at a generic data plane design from a Kubernetes perspective, right? So this is typically a single node in a cluster. So a cluster is typically you have a bunch of nodes. So let's take up a single node, which will have a certain devices, which is like ETH0, tunnel interfaces are your devices, or CalX, right? And your pods are typically connected to a host namespace via the vEth, right? So there is a vEth connected to the pod, and the vEth, which is CalIX that I was talking about, is connected to the host interface, right? And you can typically have two things, right? One is an ingress point and an ingress point, right? And you attach your program to ingress and egress for all the devices that you are interested in, right? Where you want to like add the eBPF code, wherever you are interested, you want to attach a program there, right? And when it receives it, the program sitting at an ingress point can look at that packet and say, okay, this packet, there is a service running in my node itself, so I can actually do a DNAT or send it to the pod 1 directly. And similarly, if it is to the neighboring node, okay, if it's an IP in packet, IP packet, then it can parse the IP in IP, then it can send it to the tunnel interface, which also has a eBPF, which can then decide where do I need to forward the packet to, right? So the interesting thing is because in Kubernetes, the way you interact with the pods are through services, because that's the simplest way you can actually interact with the pod, right? Any pod is exposed via the services, right? How do you do it? Because you're typically bypassing your IP tables, how are you going to do it, right? Till now, the kube proxy was the one which was taking care of inserting the rules and saying that, okay, where is my service running, where is my pods are running, okay, what should be the DNAT and source NAT that I have to do, and all those things was taken care by the kube proxy. Now you don't have the kube proxy. Who is going to do it, right? Your eBPF is going to do that. The Calico writes the eBPF data plane, and the data plane takes care of actually inserting all those rules and actually managing all those rules, right? So let's look at one use case on how the data plane, eBPF data plane actually improves, right? The Calico eBPF data plane actually improves the performance, right? So typically when I'm accessing a service, a client sitting outside uses the node port IP, okay? First it talks to the service, which then resolves it to your pod IP, right? That's the pod is the one which actually runs your application, right? Service is like a constitute where it tries to simplify it further, right? So if you take that as an example with kube proxy and source IP, right? You have a client IP. So client IP generates your request, right? That lands into your node where typically you have an ingress gateway or something you are running, which does the DNAT and a source NAT and replaces its source IP with its own IP. Okay, because your node, your service is running here, So it has to do a source NAT and the destination NAT and then send it to the node where the service is running, okay? And the packet is forwarded to the service pod IP. Now in the reverse path, the pod will perform the action, then it has to go back to the node which was originating, then from there again the reverse NATing will happen and then go back to the client, right? The disadvantage of this is the pod will not see source IP, that is it cannot see the client IP. So there might be a lot of cases where you may want the source IP visible in the service itself, in the application itself, which is not possible with the IP tables. Now the reverse path also, right, since it has to go back to the original node and then go back to your client, which basically means your latency increases, right? The entire round trip latency increases. Now how does Calico address this, right? So with the eBPF program, when the packet is received at the ingress, it looks at, it has something called a load balancing, connect time load balancing, which I'm going to talk about, and it makes a decision saying that, okay, the pod doesn't belong here, so it uses the BPF maps to decide, because BPF maps is going to store where are my services running, what are the back-end IP address and etc. That eBPF code will say, okay, it's hosted on the other node, it sends it onto the other node, okay, through your tunnel interface, and that interface is going to look at, okay, the eBPF program is going to look at that and then does a DNAT, because you're getting a service IP, so you're going to do a DNAT to your pod IP and then send it to the pod, okay. Now at this time, this can actually really see the client IP, because you're not done the source NATing, right? So then if your node is properly configured, it uses the direct server return where it can directly send it to your client. So it doesn't have to go back to the node and then go back. So that way it reduces your latency and also improves your performance as well. So that's how it benefits the Kubernetes specifically, right? I think the Cilium also does similar thing, but this is an example of how the Calico does. Okay, so this is you can go to the source to understand like how they've done the test and what are the corresponding applications that they use. Basically, the data plane is compared with respect to pod communication or the CPU, how much CPU that you are going to consume, right? So throughput wise, at a MTU of 1440, your eBPF is actually performing better, and at a higher MTU also, still the eBPF is performing better in terms of when your pod-to-pod communication is very heavy, right? And so CPU usage lower is always better. So eBPF actually consumes lower resource because it's running in the kernel and you don't have too much running in the user space, right? So and coming to the first packet latency, so eBPF also has a lower first packet latency when you compare to either IPVS or the IP tables based kubeproxy implementation. So the entire comparison is respect to how Kubernetes uses services and how the communication happens via in this one, right? So this is just a high level eBPF data plane architecture, okay? So I'm just showing the points where the hooks are been attached to. So the Calico attaches the eBPF program to the TC hooks, that is your TC eBPF hooks on the Calico interfaces. So whichever interfaces that is it's interested in, like for example, ETH, pod with interfaces as well as the physical devices, right? So whichever interfaces it's interested in and the tunnel interfaces, it attaches the eBPF for the TC at the TC point, not at the XDP, but at the TC point, right? So when it spots a packet at the TC point, so it spots it and then it handles, it looks at the maps and it hops to the faster path, right? By bypassing your IP tables and etc. Right? It bypasses the IP table and other packet processing, and it directly hands off the pod, right? So there's a pre-compiled load balancing, connect load balancing that the Calico has implemented, and the packet processing is pre-compiled and stored it in the in your BPF maps where the NAT forwarding and backend information everything is stored. So typically it uses two stores, right? One stores has the information about your services, okay? Where my services are running, what is the metadata? Because there's something called the external traffic policy, okay? In Kubernetes, if you are setting it to local, that means that the pod where your service is running, only that pod can receive the request. If it's sent to cluster, then it uses the tunnel where it doesn't matter which node it hits the traffic and it forwards to the right service, right? And a second map is stored for your backend IP address because it has to do a DNAT, right? So it stores what are the IP address of my pods, and it stores it in your another map, right? So if we expand a little bit further into a TC itself, right? It typically has a policy program. As I said, it's auto-generated, right? In this mode, you can write the policy, and the Calico converts that into an optimized eBPF code. Okay, you don't have to write; you just have to write the policy, and that converts it for you, right? And Calico uses your eBPF to store the, as I said, store the IP sets that matches to the policy selectors that you have defined in Kubernetes, right? So to improve the performance, Calico does a connect time load balancing of the, by hooking into the socket eBPF. So you can do a socket eBPF connection. So by hooking it to the socket eBPF, it can do a connect time load balancing and send to the program directly, which Dushyant was talking about the socket maps, right? Okay. So the Calico can intercept the connection attempt and configure the socket to directly talk to the backend pod. It doesn't have to go to the service now. It can directly actually send it to the backend pod directly, right? That way it can actually reduce your latency further, right? And this basically removes all your NAT overhead completely, right? And you can directly connect to your pod. Like for example, this will be very useful in terms of service meshes, right? Where you would have an NY typically connects to the pod directly, right? And just a last slide on, like, I think you should know when to use the eBPF also. I think one place where we are not, like, it's not advised to use it is when you are doing encryption and decryption for every packet that comes in, and you don't want to do encryption and decryption in your eBPF because that might increase your eBPF CPU consumption. Okay, all other things, when to use it, I think Dushyant and Dushyant has covered it, right? Like using XDP, using connect time load balancing, okay, and building a service mesh using this eBPF code, right? So I think, yeah, that's all I had. So this is, I don't know why this is gonna come on. Okay, so I just wanted to introduce the Calico eBPF. I know people, there is another session where you talk about Cilium eBPF as well, but I just wanted to introduce so that when you guys go and try it out, right, you have a base idea about, like, okay, what is Calico eBPF and what it provides for you, and especially in terms of cloud native, like if you do it in cloud native, right? That's a talk that I wanted to give just to introduce you guys to the Calico eBPF.
Thank you, Deepak. Any questions?
Hey Deepak,
Yeah, hi.
good talk. Thanks for the overview. Actually, wanted to know. So you are talking about Calico here.
Yeah.
So is this in some context where you have basically used this in Intel somewhere?
It's more like we've been trying it out because as part of the edge computing, right? So we were looking at to see which one provides like better performance and better thing for the edge use cases, right? So we just were like trying it out different like Cilium, Calico, and other things. So because there are cases where we want to have IP tables, right?
Sure.
And there are cases where we want VPP, right? So that's where we wanted to look at because it's like a pluggable, right? I can choose IP tables or this one. So that's where we were trying to experiment it. So that's where we.
So in terms of, so you mentioned edge because that makes it more interesting, right? Rather than just performance, you basically want to see resource overhead reduction, power usage reduction, and basically all those things. And in that scenario, like what basically, so have you done any study or like what have you compared on? Like is Cilium better in particular aspects or is Calico better in the other aspects? Do you know?
No, I don't want to go into that. I think probably Cilium, when they cover, I think they'll cover because Cilium is like way ahead of Calico. Calico eBPF is like new kind of a thing, right?
No, nothing in terms of like bad blood between them. I'm asking in terms of like, have you done anything like that?
Yeah, I mean, we have compared.
For my knowledge.
Yeah, most likely it's comparable in terms of performance. Even Calico actually has published the data comparing with Cilium. Cilium has published the data comparing with Calico as well, right? If you go to Cilium side, they have comparison saying that, okay, if I use pod-to-pod communication, how does Calico is performing in the same eBPF context versus this thing? It's comparable. I mean, obviously Cilium is more matured, so it will have a slighter advantage compared to this one, but yeah, it's comparable.
Thanks.
Thank you. Maybe I can go next. And again, since we are talking about Calico versus Cilium, the basic user-facing feature in the open source that I miss from Calico is the ability to send telemetry and policy violations. It's not available in open source. Cilium gives it in open source. That's the biggest difference that I feel as a user. But anyways, let's keep that aside. That's a different problem. In one of the slides, you mentioned that you can modify syscall arguments.
Yeah.
Well, how is that possible?
I mean, you can write the hooks to go tell the program saying that, okay, you connect to that. I mean, part of your program, you can tell saying that, okay, you connect to a different endpoint kind of a thing, right? I mean, it's not explored enough, but I think that's something that Calico is trying to do in terms of
Modifying syscalls is not possible, is what I feel. Because if it is possible, it enables a whole lot of options.
Okay.
And it's a security risk in other cases. But I wanted to know if there is any technique that I'm missing here.
Not really. This is something that it's part of the Calico where they were trying to do it with respect to their program. But yeah.
And the other part is Windows eBPF. You mentioned Windows eBPF. Is it already ready for networking stack?
No,
is
I
it
think
available?
eBPF is not ready yet, I think. I think they're working on it, but as I said, it supports the Windows nodes, right? But if it enables it, you can use it. That's what I meant.
Okay.
I think Brandon was talking about Windows eBPF, right? We're trying to make a standard, and he's making. Yeah, I agree. I mean, it's like if it's available, they're going to use like by default it supports it.
I wish,
Yeah.
Deepak, I'm not a networking person, but seems like there are going to be too many eBPF programs loaded into your kernel if you are using any of the tools. Is there a guarantee they're going to play along well with each other, or can you
in
figure
terms
it
of
out?
networking you're talking about? So typically, see, if you're running Calico, you only run Calico. You cannot run another CNI.
But in general, I'm asking, is there a way, can I enumerate all the eBPF program and do something and say, okay, this program is gonna reroute the packet to this and this gonna do this, and I don't know which one take precedence.
My understanding is you cannot hook two eBPF program for the same PC, right? So it should be only one.
Right. As long as the
that's
kernel
massive, right?
guarantees it.
I mean, if two people containing the same packet, I mean, it's going to be a contention, right? Who's going to handle it, right? So, I mean, there can be cases where I can write a program where I can do a copy of the packet, and then you can do it. You shouldn't want to answer that question. Theory, you can do it. I'm saying.
Not in theory. You can attach two EPF programs at the same TC hook, and you can choose their execution. So this is a problem that.
But again,
this is a good problem that you mentioned, because not all of these open source tools are compatible.
Correct.
If you load one, they all take. So in your kernel, when you attach multiple programs, they have to be told that this program takes precedence over the other.
Yeah.
So first this executes and then that executes. For that also you have to return specific return code from your program. So TC has a specific return code which when you return saying that I am done executing, allow the next program to execute, or I am done executing, either drop the packet or just stop the execution flow. So all the programs need to be compatible.
No, the question is if it's written by the same guy, I know the precedence. But if the two guys are coming and saying that, okay, I will also do it, who's going to give the precedence there, right? That's where the complexity will come, right?
Yeah.
Like for example, a vendor A comes and says, okay, I'm going to put a eBPF program at the TCU. Another guy comes and says, I will also put. Who's going to prioritize it?
Exactly. That's the point. So there are basically a couple of tools in this space which solve this. One is obviously the Leaf that tries to solve the problem at the loading time, and at runtime is where what I was mentioning, the eBPF